All right, this is a supplementary instruction video for the ARM architecture working on this SeedLab 2, which is the buffer overflow attack. So basically, this is the instruction for the core software and system security, and the lab was adopted from the SeedLab. So basically, for students using the macOS system and they're installing the ARM architecture-based Ubuntu system, you will need to refer to this video. But before that, please still check for the other video talking in the x86 architecture, because in that video, we're actually introducing how you're really going to execute the attack starting from 32-bit and then moving to the 64-bit. And for the ARM architecture, we are not going to having any like 62-bit programs in this system, so we are directly going to jump into the 64-bit. So to have a better understanding, so you may also want to check the other video. So similarly, we are going to introduce starting from the task 3 and until task 6. So we're going to demonstrate the 4 different levels on the attack, the buffer overflow attack. So the process is pretty similar, so you still have to turn off all the countermeasures. And also specifically for the macOS or for the ARM architecture, you also need to change something inside the makefile. So which is actually inside the makefile. Similarly, you are going to remove all the targets, like listing with this DBG. You only keep this stack L1 to L4 as the target, similarly to the x86 architecture. And then for the ARM architecture or for the ARC64, so they are the same thing. So you need to add another flag when compiling the program in the makefile. So this line 19 have to be added into your makefile if you are running on the macOS system, which is the ARM architecture. So this M branch protection, this is another countermeasure in the operating system to defend against the buffer overflow attack. So you also have to turn this off, otherwise you will not be able to run the attack. All right, so let's be quick. That I'm going to just like mostly focusing on the differences between the ARM architecture. So first, we're also going to do the similar thing. We're going to do the investigation, and also we have to using the make to compile all of the programs. And most importantly here is that, so the difference here is in the ARM architecture, we're not going to have any 32-bit program, which means that we're going to starting with attacking on the 64-bit machine. So let's start from doing this debug for the L1, for the level 1 attack, and I'm going to explain the different parameters here for you. So we can see here I have already compiled all of these like binaries. So all of this with the red background means that they are set UID programs. So we're going to start with removing the previous bad file and create a new one using touch command. And then we directly execute the GNU debugger for our stack L1 debug. And there are also similar things. So basically we having using the dummy function. So if you go back to check the you go back to check the shell code, the code here, the vulnerable program here. So we have this dummy function and also our buffer overflow function. So the reason is that, so in as I have introduced in the class, so the for the ARM architecture, so the stack layout is completely opposite comparing with the x86 architecture, which means that in the x86 architecture, so if you still remember the stack diagram, we are starting from the buffer, which is at the lowest end of this stack, and then the buffer will grow upward from lower address to higher address, and the return address and also the EBP pointer, so all of them are like on the higher address than the buffer, which means that when you overflow the buffer to higher address, you will eventually be able to overwrite the content in the return address area, and this will lead you to the shell code. So this is how the buffer overflow attack works. And things become different in the ARM architecture, because in the ARM architecture, the buffer will be placed in a higher address than the return address, which means that, so if you are overflowing the buffer, so the buffer, when you are overflowing it, is always going to grow upward. But in this case, the return address is lower than the buffer, which means that if you want to overflow the buffer and change your own return address in the same function, this will not work because the buffer will get farther away to the return address. So So this is the reason we're having this dummy function here. And the dummy function is also very useful when we are using this the level 4 attack. But now I'm just going to introduce why dummy function works here. So you can see here the call chain, the function call chain is that you're starting from main function and then calling the dummy function. And then the BOF, the buffer overflow function, is actually called inside the dummy function. So what are the differences here? So basically, when we're having this function call chain, it was always grows like down. So basically, you are first having this main function at the very top of the stack, and then when the main function calls the dummy function, so this is our call chain, the dummy function will be assigned with a memory block below the main function. And remember here, because we have the return address lower than our buffer, so in this case, you can consider the return address is located at the bottom of the dummy function's stack frame. So in this case, if you are going to using the dummy function to call another function, which here is our buffer overflow function, then the buffer overflow function, when you overflowing its buffer, it will be able to change the return address for the dummy function. So this is the reason we're adding another function to allow the buffer overflow attack to still work on the ARM architecture. So basically here, when you are overflowing the buffer in this vulnerable function, it will grow upward and then it will touch the return area for the dummy function. And then the dummy function's return address has been changed, which means that it will going to eventually be jumped to the shellcode. So this is the basic reason. So this will give us some of the changes when you are doing this debugging, because now you are going to set 2 different breakpoints and check the stack frames in also in a different way. And also, the name of the registers are also different in the ARM architecture. So for example, we're starting from setting up the breakpoint. We set the breakpoint. The first breakpoint will be on the dummy function. And then we are going to using next, just similarly. So this will, we need to first run the program and then we do the next. And in this case, it will going to enter the states that we are about to call the buffer overflow function. So at this moment, we can check the EBP pointer, which now was named as x29 pointer. And we also need to add another p/x. By doing this, we will be able to see the hex value, which is the correct memory address. Otherwise, it will not. You will see a decimal value that you cannot be able to translate into the hex value. And then the EBP pointer now names x29. So this is the frame pointer in ARM architecture. So we check the address. So this is E830. So this is the address for the frame pointer. And then we're going to set another breakpoint because we want to check the buffer in our BOF function. So we set the breakpoint at BOF. And then since we're in the debugging and we want to move to the next breakpoint, we want to tap continue. And then similarly, we do next, so the program will run. And in this moment, we'll be able to get the address of our buffer. So these are the 2 critical addresses we want to use to create our bat file. So we first having this buffer. The buffer is located at E7C8. And then we're also having our frame pointer at E830. So let's first calculate their offset, because the offset plus 8 will be the place of the return address. So using hex calculation, so 104. So this 104 is the offset between the x29 pointer and also the and the buffer. So because in the 64-bit machine, where the stacks are aligned with 8 bytes step, so when we need to add by 8, so this 112 will be the first parameter we are going to change in our Python file. So the offset here, is actually the offset between the start of the payload to the place that we are going to place our return address. So here the offset is equal to 112. And also, as I mentioned in the as I have already mentioned in x86 in the other video, so because in this case in the 64-bit machine, we were going to have binary zeros inside our memory. So this means that the string copy will automatically stop when they see the first binary 0. This is the reason why that we can only place the shellcode before we place the return address, because if we still place the shellcode after the return address, it will not be correctly copied into the buffer. So in this case, once we have set the offset at 112, we can only place the shellcode in a lower offset. So what could be the shellcode be placed? First, let's see that here for the ARC64, for the ARM architecture, we have 44 bytes of the return of the shellcode. So we need to give 44 bytes of the space in between this return address and the shellcode start. So the start will be equal to 112 minus 44. So in this case, we can place the start address, we can place the shellcode right below the ARM right below the return address. And then the next step, we have changed the offset, and we also changed the start address, the start offset. So the next step will be changing the return address. And similarly to the x86 architecture, whenever we're using the GNU debugger, we will going to have the stack will be like lower than we actually execute them. So when we're executing in the real environment, we need to make the address higher, make the return address higher, so it will be correctly landed into the no-op area. So let's first do some of the guess. So let's see the E7C8. So the E7C8 is our buffer, and we need to add something into there. So let's just try, for example, we can using like the decimal 160, which is in the hex value is actually the A0. So we can do. So let's see if this works. So we need to using the Python 3 to compile, to execute directly. So the Python does not have any compile. Okay. Now we have generated a bed file. So you can see this is in the ARM architecture, ARC64 architecture. The size is 517 bytes, but we only have 120 bytes usable data because after this memory address, everything will be truncated. And the shellcode, so 44 bytes, was placed at the offset of 68. And then let's try to see if this works in our level 1 attack. Yes, we're done. So in this case, once we place a 100 bytes of the offset, so if we play 100 bytes higher in this like the return address comparing with the buffer, we can correctly get the shell. However, in your real experiment, similarly, you cannot rely on the data I provided here, because you will see a completely different buffer address, completely different frame pointer address, and also the GDB, the GNU debugger, may also give you some different sizes, like the stack may shrink differently. So I really suggest you to do the test by yourself, do the trial and error. So this is widely used when we're doing a Stack Overflow attack. Do the trial and error and see what's the correct number for you in your environment. Now, if we type ID, we can see we're having this user ID, and also we have the effective user ID, EUID equal to 0, and there is a pound sign, means that we correctly get the, we successfully get the root shell. So let's move to the, let's now move to the second level. First, we need to remove the old bed file because we need to compile it again. We need to construct it again. And we first create an empty bed file so we can run the debugger. And directly we debug the stack level 2. And then for the second level, if you read for the instruction, you will see that for the second level, we do not know the specific address, or we do not know the size of the buffer, which means that we should do the guess. And in the x86 architecture, in the 32-bit machine, what we are doing is actually we are using the spray approach. However, here the spray approach will not be able to use in the ARM architecture or in any types of the 64-bit machine. It is because that, so again, we're having those binary zeros inside our return address. So if you copy the binary 0 into your buffer, if you want to place the binary 0 in your payload, the string copy will immediately stop when they see the first binary 0, which means that even you have tried to spray the return address across your payload, only the first return address will be able to be used. So this is what we are doing here. So now let's see how we can get this new buffer address for the stack level 2. And remember, because we do not know the buffer size, we cannot get the, we should not go to check the number or the address of the x29 pointer, the x29 frame pointer. So we do not need to set the breakpoint in the dummy function. So instead, we directly set the breakpoint in the buffer overflow function. And we start to run, next, and then we get the address of our buffer. So this E790, so this is the new buffer address, and then we will need to do some of the trial and error. So this is the reason is that so we cannot, because I have mentioned, because we cannot using this for loop anymore, because in this case we cannot spray the return address all across the payload. So what we can do here is that we can either write another for loop to change this offset value in an 8-byte step, or you can also just like manually change it and run it again. So here I'm just going to show you how you can manually change it and do the trial and error. So first we quit this GNU debugger, and then we also need to modify this buffer size, modify the return address slightly. So for example, we directly now we do 790, and also we plus this 100. And seeing similarly here, the 112 minus 44 equals to 68, because we only know the buffer address will be between 100 to 200. So which means that we can, with the lowest position we place our return address should be still the 112. So we cannot change the start address here, the start offset here. So basically here, we're starting for is changing. We're going to start with trying from 112. And then we're going to increase it in a step of 8. So let's first create the new payload. And then we run a stack L2. And now if you will be like, when you are running, if you are using 112, it's highly possible you will also see the return properly. This is because that we haven't successfully changed the return address. Remember, we are now using the trial and error. We have to move the return address across our payload, and eventually we are going to reach the correct place, and the return address has been changed into our no-app sled and to our shellcode. So now let's add them by the 8-byte step. So now 120. We still need to save this Python file and create a new bed file. We'll create a new payload. You can see 120 is not large enough as well, so we try 128. Not large enough. So we try 136. I have to store them. Not enough. Try 144. Not enough. Try 152. Not enough. Try 160. Not enough. Try 168. And very luckily, I directly entered into the shellcode, into the root shell without modifying this, without further modifying the return address. So when you are working on that, you may not see in the scenario. So for example, if I set this return address if I set this offset to something else, for example, we set to 0x50 F0. So you may be able to see something like this, illegal instruction. So this means that once you have changed the status from return properly to illegal instruction, which means that you have successfully changed the return address, you have hijacked the control flow, and then you will need to investigate what is the correct number for the return address. All right. So let's change it back to 0x80. This is a good number, I love it. And then we have done with the L2, the level 2 attack. And this is actually matched with the level 1 and 2 in the 32-bit machine, but now you are already using the approach on the 64-bit. So in the L3, the level 3 attack, which when the x86 machine changed to 64-bit, you are also going to do the similar thing. So this is basically similar, almost the same with your level 1 attack. But the only changes here is that so you have changed the stack size, the buffer size has become larger. All right, so let's see. Let's also see what will going to be changed. So similarly, we remove the bad file, and we create a new empty bad file, and we do the debugger. And then now, because we already know, so now in this case we're back to know the buffer size, so we have to get the address of our x29 pointer, which means that we need to set 2 breakpoints. The first one will be in the dummy function. Run. This is the pointer. This is the frame pointer, and then we set another breakpoint in our overflow function. We tap continue, next, and then we get the address of our buffer. So here's the new buffer address and the new frame pointer address. So now we need to calculate their offset. So again, we can directly using this calculator. Select hexadecimal 768 830 minus 768. So this is actually 200 bytes of the offset. So to correctly place the return address, as you know, so you have to add 8 to this offset because the return address is 8 bytes higher than the frame pointer. So now we first replace this to 208, and then because we have larger space here, so we can still keep the start as so we can still keep the shellcode and this address, but it's actually we can slightly make it bigger. So this gives us a higher chance to correctly land into the no-op sled, because so the no-op sled after the buffer, the no-op sled after the shellcode will not be useful. So if you still remember, no-op sled is actually going to continue to the next thread, the next command, which means that so it will only grow, or it will only move from lower address to higher address. So which means that you will not. There's useless if you have any no-op sled after your shellcode. So because here we're having the 208 as our offset, so we have larger space, so we can directly put here as 208 minus 44, which the 44 is the length of our shellcode. And now we also need to modify the return address. So return address, now we still check for the buffer, and we can find here is the new buffer address 768. And let's first try if this magic number still works. We still need to compile. We still need to run the Python code to create a bad file. So now you can see the shellcode 44 bytes are located at offset 164. And then we try to run the L3 directly. And again, very luckily, we have entered into our root shell. You can see it here, you can still see the pound sign. So the main idea is that you are going to correctly change the offset, and you can also make some changes if you want to the start address. And then the most importantly, you always need to do some of the trial and error to see if you can correctly make the return address land into the no-op sled. So this is for our level 3 on the ARM architecture, and then we can do on the level 4. So the level 4, will be the same thing as the x86 architecture. So we do have a smaller, very small buffer size, which is only 10 bytes, and cannot contain our 44-byte shellcode. So what we are doing here is that we are going to make a good use of our dummy function again, because here, when the dummy function was called, it was passed with this string. The string will have to be first copied into dummy function stack, and then it will be passed to the BOF, to the buffer overflow function, as an argument. So this means that the string, even it cannot be completely copied into the buffer overflow function, it still locates somewhere on the memory, and this is what we want to use. So again, similarly, we remove the old byte file, we do the debugging again. And we also need to set 2 breakpoints. So now here we can see the differences. So we have the frame pointer located at E830 and our buffer located at E820. So which means that the offset here is a hex number of 10, which in the decimal is 16. And we will need to add this one as the, and then we need to add 8 into our return address. We need to add 8, and this will be as our offset, because now the 16 plus 8, 24. This is our offset between the buffer to the return address. So here on the payload on the 24, this is where we are going to store our. This is where we're going to store our return address. And you may also want to know that you may also want to know that why the smaller buffer size cannot contain the shellcode, because the buffer size, the smaller buffer size, is only used to define where the return address should be placed. And this is actually not a big problem in a 32-bit machine. So in a 32-bit machine, it is actually that the shellcode is placed above the return address, which means that even if you are having a smaller buffer, this doesn't really matter, because eventually you can jump to somewhere higher. However, we are using this level 4 for 64-bit machine. It is because that, so in this case, in 64-bit machine, you have to place the shellcode in between the buffer start and the return address. So a smaller buffer will not allow you to place 44 bytes of the shellcode into this 24 bytes of space. So this comes with a challenge. And as I mentioned, so we have the dummy function stored the string somewhere else in the memory. So we can check this string by directly using p_str. This will give you another memory address, EC68. So let's see where the EC68 are located. And higher than the E820. All right, so we can see, we can do the calculation. So you can see it is 1032 bytes higher than our buffer. So this is actually also fits with our assumption, right? So in the function call chain, because the dummy function was called earlier than the BOF, the buffer overflow function, so the content in that function will be on a higher address than your BOF function. So this is the key point. So we're having this everything here started. So the start area. So now we can place the start. So we do not need to like place anything of this start, because we do not need to change the start, because in this case we are like directly having all of this string. So we are not using a overflow like vulnerability. We are storing the whole string in the memory legitimately. So this means that we can place wherever we can place the shellcode wherever we want. So in this case, we can keep this value intact and we don't change it. And then the only thing we have to change in our string, in our return address, is actually we need to return to this string, which is previously stored in the memory, already saved in the memory. So EC68. And we continue to using this one. We need to add 100 bytes. So this is the offset when we are removing the debugger. Let's see if it works. And now, instead of jumping to your own address, to your own memory, to your own buffer, to your own string, so now you are going to jump to the other string, like located in another function. So let's try if it works. Bus error. So let's see what could be happening here. So we're having this 0x80, And then we are going to, so now in this case, we may need to change some of this thing. We may need to change the address. For example, if we make it smaller, let's see. Yes, we make it bigger. So in this case, let's see, this is how you are going to do the trial and error. So when we make this magic number larger, so which means that when we are going to, when we are giving like a higher address, we're giving higher space, like higher offsets to your starting address, you will be able to get into the correct no-op area, and then you're going to give the, you will be able to get the root shell. So this will be the everything for introduction on the ARM architecture, and this is for the level 1 to level 4. Hope this will help. And I'm not going to do the instruction for the later assignments. I really hope you can do the later tasks by yourself, like for example defeating different types of this address randomization, or like the dashes countermeasure. So basically the whole idea of these two videos is like you may be able to get a better understanding on what you are really dealing with, what you are the memory address, how you are going to play with this memory address, how you're going to play with this like a stack structure. So again, still, if you have anything unclear when you are watching this video, if you are using a Mac computer, so I really suggest you to watch the other video for the x86 architecture, so you may get a better understanding on how these 4 tasks are really working. All right, yeah, that will be the information. Thank you.